Welcome back to the Deep Dive. Today we're tackling, well, one of the biggest questions out there, fueled by decades of science fiction. Where are all the time travelers?
It's a classic, isn't it?
Totally. I mean, Stephen Hawking famously threw that party back in 2009, right? Champagne, everything. But he only sent the invites after the party.
And nobody showed up.
Exactly. No one came, as the paper we're looking at today puts it. It just feels like, if time travel ever gets invented, shouldn't we see someone? Shouldn't our future be full of them?
It does seem intuitive. And physics, well, it doesn't strictly forbid it.
Right.
You've got things like Gödel metrics, closed time-like curves in general relativity. They're theoretical, sure, but the possibility seems allowed.
So why the silence? Especially with potentially trillions of humans in the future.
Precisely. It's a genuine paradox.
Which brings us to this fascinating new paper by Andrew Jackson. It's called Where Are All the Tourists from 3025? And it offers this really surprising take.
Oh, it really does.
It basically says, time travel, it's possible. Theoretically, technologically, possible. But we still won't see tourists because the act of time travel itself, well, it stops itself from happening. It's self-suppressing.
And that's the core insight for you right there. The paper models a universe where time travel is possible, but it inherently leads to its own erasure. That's the surprising answer to Hawking's empty party.
Okay, let's unpack this. A self-suppressing mechanism. How does that even work?
Well, the paper builds this model. It starts with the concept of possible world. All the ways things could be.
Right, infinite possibilities. Sounds complicated.
It would be. So the paper simplifies this. It groups timelines into what it calls macrostates.
Good macros.
Yeah, think of it like this. A macrostate isn't defined by, who won World War II or whether you had toast for breakfast. It's defined only by one number.
Okay, which number?
The construction number.
Yeah.
Simply put, it's the total count of individual time machines ever built in that specific timeline. That's it. The model only cares about that number.
Huh. So a timeline where 10 time machines were built is in macrostate 10, regardless of anything else that happened.
Exactly. It's a clever way to abstract things. And then it models how timelines jump between these macrostates.
Using a Markov chain, right? A continuous time Markov chain.
No, that's the one. It's a mathematical tool to model systems moving between states randomly over time. And the key assumption is how these transitions happen.
Which is?
Transitions between macrostates, changing the timeline's fundamental character in this model, only happen when that construction number changes by exactly 1. Either someone builds a new machine, pushing the number up.
Or somehow an existing machine gets, unbuilt? Removed from history?
Sort of, yeah. Its existence is effectively erased from that timeline's history, pushing the number down by 1.
Okay, but here's the kicker, right? The rate of these changes.
Ah, yes. This is where it gets really interesting. The rate at which these timeline shifts happen, the transitions between macrostates, it increases the higher the construction number is.
So the more time machines exist,
the faster the timeline jumps around, the more unstable it becomes. The paper uses this great analogy: more butterflies flapping their wings. More time travel activity means a vastly greater potential for changes, for things to be rewritten.
And conversely, if the construction number is 0,
then the rate of transition out of that state is 0. No time machines means no way to initiate changes to the timeline. It's a stable state, a dead end for timeline changes.
Okay, I think I'm following. More time machines equals more chaos, more rewriting of history. 0 machines equals stability. But then there's this other concept, orthogonal time. That's tricky.
It is a bit mind-bending, yeah. Think about it from the perspective of someone outside the timeline, or maybe just a non-traveler within it. A time traveler could, from their own point of view, spend, say, 100 years bouncing around history.
Making changes, fixing things, breaking things.
Exactly. But for us, the observers who aren't doing the traveling, how long does that century of their activity take on our clock?
Instantaneously. If they jump back to the moment they left?
Precisely. From our perspective, they can experience potentially infinite amounts of their own time, making potentially infinite changes, all of which register in our timeline. Well, instantly. It's orthogonal, perpendicular to our normal flow of time.
Okay, wow. Infinite changes, instantly. What does that do to the model?
It's absolutely crucial. It means we, as the non-travelers living through history, never actually experience the messy intermediate steps. We don't see timeline A get changed to timeline B, then C, then back to A, then to D.
We just see the final result.
We only ever perceive the asymptotic limit, the ultimate state the timeline settles into after all that instantaneous churning and rewriting is done. All the intermediate fluctuations, the timelines that could have been but were undone, they are, from our perspective, effectively prevented from ever happening.
So connect the dots for me. We have this Markov chain, where more machines mean faster changes.
Right.
And we have orthogonal time, meaning infinite changes happen instantly from our view. What's the inevitable outcome?
The inevitable outcome, which the paper proves analytically, is that as this orthogonal time goes towards infinity, as the system has limitless potential to rewrite itself, the probability shifts.
Guess where?
It shifts overwhelmingly towards one specific state. The probability of the system being in the macrostate with construction number 0.
No time machines ever built.
That probability approaches 1. It becomes almost certain. And conversely, the probability of being in any other macrostate, any timeline where time machines do exist, even just 1 approaches 0.
So the universe, or the timeline, naturally just erases time travel from its own history, like an immune response.
That's a great way to put it. The very act of time travel introduces so much instability that the timeline keeps rewriting itself until it lands on a stable configuration, and the only truly stable configuration is the one where time travel never got started in the first place.
That is quite an idea. The paper backs this up with simulations, right, to show how it plays out.
Yes, exactly. They ran numerical simulations that confirm the analytical results beautifully. For example, they show a simple case with just, say, 5 possible macrostates starting in state 3.
So starting with 3 time machines existing.
Right. And you see the probability of being in state 3 decays incredibly quickly. There's a brief moment where states 1, 2, maybe 4 flicker into existence with some probability.
As the timeline shifts around.
But then very, very rapidly, the probability drains out of all the states with machines and piles up entirely onto state 0. It converges fast.
What if you allow for more possible time machines? Like hundreds. Does that change things?
Good question. They simulated that too, like 500 macrostates, starting again at 3. The convergence to 0 is definitely slower. The probability spreads out more initially among the many intermediate states.
It's longer to find that stable 0 state.
Exactly. But the end result, still the same. Asymptotic probability of 0 machines is still 1. It just takes longer to get there.
And if you start with lots of time machines, say state 100 out of 500.
Then the initial decay of that starting state is even faster and incredibly steep. But the overall convergence to the final 0 state takes much, much longer because the probability has to diffuse down through all those intermediate states first.
But it still gets there.
It still gets there. The asymptotic behavior is robust. No matter where you start, no matter how many machines you assume could potentially exist, the system always, inevitably, tends towards the state with 0 time machines.
So the conclusion is pretty stark. Time travel is inherently self-suppressing.
That's the core takeaway. The timeline just won't tolerate it. It rewrites itself until the time machines are gone.
Okay, but how does this stack up against other explanations? The simpler ones. Maybe time travel is just impossible. Occam's razor.
That's always been the default, hasn't it? It's physically impossible for some reason we don't fully understand yet. Or maybe something like Novikov's self-consistency principle holds. You can travel back, but you can only do things that were already part of history, preventing paradoxes.
Right, or maybe Deutsch's quantum ideas about parallel universes resolving paradoxes, or Hawking's chronology protection conjecture, that physics itself conspires against it.
Exactly. Those usually involve some physical barrier or rule. What's really different about this paper's model is that it doesn't need any new physics. It assumes time travel is possible according to known physics, like GR.
It doesn't say you can't build a machine.
No. It says, go ahead, build it. But the consequence of building it and using it is this dynamic instability that leads to its own erasure from the timeline. It's not a prohibition, it's an emergent property of the system's dynamics.
Almost like a system settling into its lowest energy state in thermodynamics.
That's a perfect analogy. The state with 0 time machines is the stable, low-energy ground state for the timeline itself. Any other state is excited, unstable, and decays back to 0.
That really does flip the perspective. It's not impossible, it's just terminally unstable. So for us, for you listening, what are the big implications here?
Well, the most direct implication is pretty clear. If this model holds any water, we shouldn't be holding our breath waiting for tourists from 3025.
Or any other future time.
Or any other time, yeah. And maybe, more profoundly, it suggests that time travel might just not be a feature we should expect our own future descendants to develop and use widely. The timeline itself might prevent it from ever becoming commonplace.
The model mentions a parameter, beta, that scales the transition rates. Does that offer any loopholes? Could future societies manipulate that?
That's an interesting point the paper touches on. Beta scales how fast the transitions happen, but crucially, it doesn't change the direction. The system still tends towards zero machines unless beta itself is somehow forced to be exactly zero.
Which would mean stopping all timeline changes.
Yeah. Effectively, yes. The paper kind of frames beta as potentially a sociological measure. Maybe different factions could try to suppress changes, try to force beta to zero to preserve their timeline. But the model doesn't really explore that conflict scenario deeply. It suggests it's unlikely to fundamentally change the outcome unless someone achieves perfect control.
What about the assumption of orthogonal time going to infinity? That feels like it relies on time machines basically running forever without breaking down. Is that realistic?
That's a very fair practical point. Can machines really run indefinitely to allow for infinite rewriting? The paper does address this.
How?
Well, first, it points to historical trends. Think about complex machines like cars. Their average lifespan, their reliability has increased dramatically over, say, the last 50 or 100 years.
True.
Project that trend forward 1,000 years, add potential breakthroughs in materials science, maybe even self-repairing tech inspired by biology. It's not implausible that future machines could have operational lifespans that are effectively infinite for the purposes of this model.
Or they could just return for maintenance.
That too. A time machine could potentially return to its point of origin for repairs. Or even, and this is a wild thought from the paper, rewrite the timeline slightly to acquire the resources needed for its own maintenance, essentially bootstrapping itself indefinitely.
Okay, that's bending my brain a bit. Rewriting time to get spare parts.
It shows how the model's core logic can accommodate some of those practical concerns, even if it sounds like sci-fi.
So wrapping up, this is definitely speculative, no doubt about it, but it offers a really thought-provoking, completely different kind of answer to the Fermi Paradox of time travel.
It really does. Instead of saying it's impossible, it says it's so possible it cancels itself out. It shifts the paradigm.
It suggests the silence from the future isn't proof of impossibility, but maybe proof of instability. That was a deep dive into what happens when time travel might just be too powerful for its own good.
It makes you reconsider the nature of possibility itself, doesn't it? How the dynamics of a system can lead to really counterintuitive, large-scale outcomes.
Absolutely. A universe that automatically edits out its own most reality-bending technology. Wild. We hope this exploration gave you some food for thought, maybe a few of those aha moments.
And maybe leaves you with this question. If time travel inherently erases itself, could advanced civilizations discover it, use it briefly, and then inevitably cause their own timeline to settle into one where they never discovered it at all? A kind of built-in great filter for timeline meddling.
Ooh, that's a heavy one to ponder. Till next time, keep exploring those deep questions.